Okay, so there are Little Man Computer instructions. Okay. Unfortunately, unlike every other subject, you don't get any like crib books or crib sheets. Like you get formula books and things for everyone else. So you have actually got to remember them. Right. So we also had DAT. People kept saying DAT. Why have I left that? It's not an instruction. It does not get converted into machine code. There is no equivalent machine. What is it? So well, it's basically it allows us to label something as a piece of data, which is why it's called DAT. Right. What is the program that takes this language and turns it into machine code? What's that program called? What's the translator called? Begins with A. Assembler. An assembler takes an assembly language program and converts it into machine code. Right. That isn't an instruction to the CPU, it's an instruction to the assembler. We call these things directives. It's an order. So that is actually an assembler directive. Now, in Little Man Computer, we're limited. This is the only directive there is. But in real assemblers, you have loads of different directives. And we'll do a little bit of that when we come back after half term. Okay, so that's all we've got to work off. So we can add stuff, subtract stuff, we can load and save stuff, and we can do some basic comparisons. That is all we can build all our solutions from. Now, I gave you a question the other day, multiply two numbers without multiplication. So 3, let's have a look at 3 times 4, and let's try and break this down. Okay, so to create a program that can multiply two numbers together, the first thing we've got to do is input the numbers. So this is the sort of decomposition we've got to do. So we've got to input two numbers. If we was doing it in Python or some other high-level language, we might put some rubbish like this. We might say n1 equals input and n2 equals input. What are we doing with those two statements? We're calling an input function that miraculously gets us the input. But what's the other part of the statement? What's happening here? What's all this junk? Yeah, correct. We're assigning a value. How do we do assignment in Little Man Computer? No. Store. Correct. Okay, so we can do the same thing. So inputting numbers is always going to be of this form. It's going to be imp and then store. So imp, remember, places a value in the accumulator. So imp ends up in the accumulator. We need to then write whatever's in the accumulator to a memory location, which is what an assignment operation is. So we would do store. And then we need to say where. So we would have a labeled address. So we might actually call these N1. And then we'd have somewhere down here, N1 DAT. And we just label it as a data location. And then we'd have to get the other input. So we go input, and then we'd store in N2. So N2 again, we'd have something like that. So that's the logic that you're always going to have in Little Man Computer if you want to deal with input and storage. Now, can you see what the difference? This is over here, this is high level language code. I know it's pseudocode, but it could actually be Python. So this is our high level language code. Can you see the difference straight away between the low level language code? What's an obvious difference? Yeah, longer. There's more steps involved. What's quite interesting is there's actually probably more steps here. But when we're writing it, we write it as one long statement. But actually, there's multiple steps going on. There's an input function runs, gets hold of some value. When that value gets returned, we say, oh, store it in a memory location. So it is actually internally doing this. But as a high-level language, we don't have to worry about how internally it all happens. We just magically go, there's a memory location called N1, lob that, whatever comes back from input. So the high-level language stuff is simpler. We have to think a little bit more nuts and bolts. Okay? And we have to think in the language of Little Man Computer. So multiplying two numbers, it's going to start with something like that. Now, the actual process of multiplying, so if we've got N1 and N2, so that was 3 and that is 4, and we want to, what's the answer if we multiply them together? 12. Yeah, so we want to get to 12. Now, we can do that by going 4 plus 4 plus 4, can't we? Yeah. What's the relationship between that and the other input? This is what we've got to try and really get down to doing. Looking for relationships between numbers and data items. So what's the relationship between 4 plus 4 plus 4 and the other input? What's the amount of times? You've got to be really specific. Right, so there are 3 4s in that statement. Yeah? Right. That's not the relationship we're looking for. What's the relationship we're looking for? There is another relationship. Well, no, that's just switching it around, man. Right, that's the more interesting thing. How many operations am I doing? So I have actually got, let me do it in red. I have got an addition and an addition. 2 of them. What's the relationship between 2 and the other number? Yeah. So actually 2, and this is how your brain's got to start working. You're going 2 is actually N1 minus 1. So if I start with a 4 and then I add 4 on 2 more times, I will get the answer I want. So that starts giving me a process. So to try and take that process, what I might do is say, right, so load to the accumulator the value of N2. And then what I want to do is I want to do this, but I've got to be able to control it. So let's just raw do it. So to implement this specific one, I would say add N2. So that's one of those. And add N2. And that'll give me the 12, won't it? Right. So the trick is, how do I do this if I start changing the value of N1? So how can I do that? I'm doing this. I'm looking for another pattern now. So I'm doing something repeatedly. So when we say repeat, what's the correct term for repeating? Begins with I. Iteration. We have actually got an iteration. Right. In Little Man Computer, we've only got one way of doing an iteration. And that's using conditions, because that's all we've got. Now, we can provide conditions to do counting. So if we look at N1, so I might do something like this. I might load up N1, which was 3, and I might subtract. But I've got to subtract 1, so I'll have to have a variable called 1 that's got 1 in it. So somewhere in my code, I'm going to have 1 dat 1. This is the weird thing you got to get used to. No constants. You've got no constants. See, everything's a variable. Right. So if I subtract 1 from 3, what value do I get? What value do I get if I subtract 1 from 3? It's not a trick question. 2. Right. So what I could do is something like this. So I could say, right, okay, I'm not going to write code here. I'm just going to put a statement. Right. So that not 0, or it's positive still. So what I'm going to do is I'm going to add n2, but I can't do that. I can't just add n2 because what I've got in my accumulator is n1. So what I need to do is make sure I save it. So I need to save the 2 back to n. Yeah. Then I can load up my value for whatever my total is going to be. Then I can add my n2. Then I need to store that again in total. Total. But then I want to do this bit again. So I'm tracking this counter. So I need to now go from here all the way and do this bit again. What instruction have we got that'll allow us to go back up to a previous instruction? Which one? Why? Why BRA? What does BRA mean? Yeah, branch always. So it says, when you hit this instruction, do what it says. So we would say BRA, and then we need an address. So we use a symbol again. So I'm going to call it count. So I'm going to label this location as count. Now the key thing here is that I'm having to make sure, because I've only got one accumulator, so I've only got one register that I can do maths with, I've got to make sure that I save things before I load new things in. Again, this is something you do not think about at all in high-level languages. So this is the bit, this is the hard bit. So I've saved it here, so I've saved again. I don't know whether this is going to give me the right answer. I might have to do something else first. All right, so I load up N1. So previously I saved that, and it was 2. So when I load it up and subtract, what's it going to be? 1. So then it becomes 1. It's still not 0, so I'm going to do all this again. All right, so I've added twice. Depends what total was set to at the start. This. Right, so I've added twice. Let's assume total was 0. So total at this point, after we've run this twice, should be, hopefully, 8. Then I'm going to go back up, and I'm going to load M1. So I load it up, and it's going to be 1. Subtract 1, what's its value going to be? 0. Now, that's when we want to stop. Or do we want to stop? Do we want to run this one more time? What's the answer supposed to be? 3 times 4? 12. Right. We've actually got 0. And we've got a branch instruction. So it might be, how can we fiddle this then so that we stop at this point? I've done 2 add operations. So let's have a look at what that little rubbish I wrote was. I said 4 plus 4 plus 4. If I start total off with 4, so I load up here. So if I say LDAN2 store total, total, before I start this, then here this would have been 4, then it'll be 8, then it'll be 12. It's all about setting data up. Okay, so theoretically, this bit here, instead of doing that like little bit of English, I could actually say branch if it's got to 0, this value of n1, to finished, which would be down here somewhere. And then I'd have halt, or I'd output my number or something. Okay, so let's try and produce an entire program then. So we've got to input numbers. So we're going to input our first number. So we do imp, and we save that in n1. So I'm going to store that in n1. Then I'm going to get my second number, and I'm going to store it in n2. But I also want to put it in total. And this is the nice thing, because we've got complete control here. We know that the value we want to store is also still in the accumulator. So I can do 2 different store operations and store that in total. So I end up with some of the you can actually do this in some language. I don't know whether you can do it in Python, but you can do it in C++ and C#. You can actually do n1 equals imp, and you can actually do in those languages total equals n2 equals imp. So you can actually write that in some languages, because they like go, yeah, we can get the compiler to do something clever there and write the instructions. So I don't have to keep reinventing things. I don't have to ask for the input again. I just say, oh, I've already got it in the accumulator still. Just write it out again. It hasn't left the accumulator. It's a copy. Everything is copied. Like when you were doing your bubble sorts at GCSE, you might have been rubbing out and things like that, but you're not. You're just overwriting values. Things that are still sat in memory. When we did the stack, which we will come back to after half term, when we move the stack pointer, we're not deleting values that are in memory. They're still there. Hackers love this sort of stuff. That's what they're looking for, because things aren't cleared. So you start seeing things sprayed around in memory. Okay, right. So that's our input setup. So the next bit then is just to do. We've done that bit. We just got to start this loop out. So let's do a label called loop, and that's where we're going to load up. So you've got to keep track in your head what's where. So we need to load up. So we're going to say LDA N1, load up N1. We want to subtract 1. So we're going to say sub 1. Now, we have now got 4 variables there. So at the bottom of our program, we need to put these statements. So we're going to have N1, and we're going to say dat, and it doesn't matter what's in there because it's going to get overwritten. N2, dat, and again, we don't care what's in there. I'm just putting a 0. I'm not writing phi, if anyone thinks I'm doing a drunken phi, which I could be. We need that value for 1. And this for me is the hardest thing to get your head around. That it's like, what? I haven't got a constant. I can't just say subtract 1. I have to say subtract the variable 1, which in has to have a 1. If I put the wrong number in there, I screw it all up. And I want my total. And again, my total, I don't care, because it's going to get written into straight away. So at the bottom of my code, I'm going to have those data items. Okay, so that's our subtract 1, and we're going to keep doing that until we get to 0. So we're going to say, oh, if it's 0, go to finish. I don't know where finish is going to be yet, because it's going to be at the end of this bit of code. So this bit is the addition calculation. So just looking straight back, all we did, we needed to make sure that we stored the value of n1 before we carry on, because it's in the accumulator. So we need to write that back. So we're going to say store n1. If I don't do that bit, then I'll just constantly be subtracting 1 from the value 3. And I'll go, it's not working. Yeah, because you didn't save it back. There is no equivalent in assembler. Well, there is in proper. In little man computer, there's no equivalent of saying, or that. Most CPUs do have that, ink and deck instructions. but we're having to do it the long-winded way. So we store it to make sure that we got rid. Then we load up our total, and we add on our 4. So we're doing add the other one back on again now. So we started off with 1, we're adding on. So it's going to say add n2, and then we're going to store it. You'll see a lot of that sort of structure in your Little Man Computer programs where you do an operation, but then you store it immediately. Okay. Yeah, I've got a store and tell. That would have been an interesting bug. What would it have done? I'd have done an exponent, wouldn't it? Because I'd have gone, then it's 8, then I added it. No, it would have actually probably worked and I wouldn't have noticed it. Terrible bug. Yeah, that's an insidious bug. That is. Right. So we've done load, do the arithmetic, store. Okay, which is the equivalent of saying A equals A plus 1. So we like load it up, add 1 to it, store it. So that's a direct equivalent. But high level language, 1 instruction. Low level language, 3 instructions. Right, so we then need to put our branch and we go back up to our loop. So that's that section finished. So we start with this little linear bit at the start where we just set things up, do some testing, and we produce a loop. And you often find this weird structure in assembly language where you have a loop with a jump out part way through. You don't do the jump out at the start generally. So you end up with this weird structure in assembly language where we do something and then we drop out. But you tend to not write loops. Loops don't look like that in high level languages. Something happens at the top. When you write a while loop, it's at the top, isn't it? The test is at the top. And then it comes out. It's all on one line. But in assembly, it can't all be on one line. Right, so that's the structure of that. And then we can put our finish. So what I'm going to do for my finish, going to have two. Well, I want to actually output the total. Now it looks, if you just look at the code as it is, you think, oh, the total's in A. But it isn't because we went back up there first, didn't we? So what was in there was whatever the counter was. It should be a 0. So what I've got to do to output it, I've got to load it back up. So I load up my total. And then I'm going to say out. And then I'm going to finish with halt. Right. Have a go at whacking that in to Little Man Computer, please. Oops. I'll zoom out so you can see it all. I am recording this, so I'll stop that one there because I want to get you to practice doing loops, basically. And do some of those things that you did in the very first Python lessons where you had to output 10 numbers and junk like that.